back to the chemical kinetics topic. We were studying this Arrhenius equation. Arrhenius equation. This Arrhenius equation is used to study the effect of temperature on the rate of reaction. So, if you recall, we have this equation K is equal to A into e to the power minus EA by RT, where K is velocity constant, A is Arrhenius constant, EA energy of activation, R is gas constant, T is temperature, and e to the power minus EA by RT indicates fraction of molecules possessing energy of activation. So to understand this energy of activation and fraction of molecules possessing energy of activation, let us consider this reaction path. Say for example, we have a reaction A giving rise to B. If you draw the graph of this reaction path, this is reaction path and this is energy. When we consider this reactant and product having different energies, assume that this is the reactant A having energy equal to this much. Then if assume that product is having the higher energy, then we know that A is converted to B, but not directly, it follows a certain mechanism. So that mechanism or reaction path can be indicated by this curve. Okay. Where this curve indicates the follow of this reaction via this process, this path. So A is first converted to some other intermediate product, then it is converted to product. So this is intermediate, that is called as the activated molecule. Activated molecule. So to go to this activated molecule, these reactants must absorb energy equal to this difference. So this is named as energy of activation. The energy possessed by the activated molecules is called threshold energy. Threshold energy. But energy possessed by the reactant molecules will always be less than the threshold energy. All these reactant molecules will not take part in the reaction. Only those molecules which reach this activated state or threshold energy will take part in the reaction. Okay, so to absorb this much energy, the reactant molecules must absorb this energy. It depends on the temperature that we supply or heat that we supply. As more and more temperature is increased or heat is supplied, more and more molecules will absorb this much energy, reach this activated state. Then they will lose certain amount of energy giving rise to product. That we will study later. So we can define as energy absorbed by the reactant molecules. By the reactant molecules before taking part in a reaction. Before taking part in a reaction is called energy of activation. Is called energy of activation. So that is indicated as EA. If you consider the reverse reaction, assume that B is converted to A. Again B is not directly converted to A, it has to pass through certain mechanism. So this energy difference between the product and the activated state is named as E-A. It is energy of activation for the reverse reaction. Now to calculate this energy of activation, we make use of this equation, that is Arrhenius equation. For this equation, that is K is equal to A into e to the power minus EA by RT, you apply logarithm. Apply log. We get this ln K is equal to ln A minus EA by RT. Here ln stands for logarithm to the base E. ln stands for logarithm to the base E. When we take this logarithm to the base E of K, it will become ln A minus EA by RT, because ln e to the base e or log e to the base e is equal to 1. Therefore we have this e to the log e to the base e is equal to 1 into e minus ea by rt. Now you convert this to the natural logarithms, logarithm to the base 10 of k. To do that we have to multiply with 2.303. So to convert this ln to the base e to ln logarithm to the base 10, we have to multiply with 2.303 log k to the base 10. Similarly we have on the other side 2.303 log a minus ea by 2 rt. Whole equation you divide by 2.303, we have this log k is equal to log a minus ea by 2.303 r into 1 by t. There are two methods to calculate the energy of activation by using this equation. Assume that this is equation number 2, because we start with this equation number 1, that is Arrhenius equation. Now you take this equation, this is of the form y is equal to mx plus c. Here c stands for logarithm to the base a to the base 10 of a, and m is nothing but slope of the equation minus ea by 2.303r. So this y is log k, and x is 1 by t. X is equal to 1 by t. So if you draw the graph of log k versus 1 by t, y is equal to mx plus c is an equation of a straight line. Therefore log k to 1 by t graph will be a straight line with equal to minus ea by 2.303r as a slope. So this is the straight line. Here slope corresponds to minus ea by 2.303r. And if you extend this line, this intercept corresponds to log a. So we can calculate Arrhenius constant log a that is from the intercept, and slope is equal to minus ea by 2.303r. From this slope we can calculate energy of activation. If R is used as 8.314 joule per Kelvin per mole, then EA will be in terms of joules. If R is equal to 2 calories, then EA will be in calories. So like that we can calculate the energy of activation, and this method is called the graphical method. Okay, there is one more method, that is by using the same equation at two different temperatures we can calculate the energy of activation. So let me take that. This is graphical method. Now let us take the other method. Suppose you write the equation log k is equal to log a minus ea by 2.303r into 1 by t. Same equation I am rewriting. If you write the same equation at two different temperatures, assume that at a temperature T1, if this velocity constant is k1, then we write log k1 is equal to log a minus ea by 2.303r into 1 by t1. Let us say this is equation number 3. Similarly, at a temperature T2, if you take this logarithm of k2, this will be equal to log a minus ea by 2.303r into 1 by t2. This is equation number 4, assume. Then take the difference of these two. So here we have to make one assumption as made by the Arrhenius. A is a constant in the given temperature range of T1 and T2. So assuming that A is a constant, then we can take the difference of these two as log k2 minus log k1. Log A gets cancelled, minus ea by 2.303r 1 by T2 minus 1 by T1, or log K2 divided by K1. Here log A minus log B rule we are using. Log A minus log B is equal to log A by B. That is equal to, I am taking this minus sign into the bracket. Now we are having EA by 2.303R into 1 by T1 minus 1 by T2. Again, if you further simplify, log K2 by K1 is equal to EA by 2.303R into T2 minus T1 divided by T1 T2. Using this we can calculate energy of activation if K1 and K2 are known at T1 and T2, two temperatures. Okay, so one is graphical method that we have already studied. The second one is by using this equation we can calculate the energy of activation knowing the velocity constants at two temperatures. Here one thing you remember, as we know, when the temperature is increased by 10 degrees, this K2 by K1 ratio will be almost 2 or 3. So using that temperature coefficient as 2 or 3, we can easily calculate energy of activation for a given reaction. So how to calculate it, and let us take some numericals based on this one as well as the previous topic, that is half-life period, in the next video. Thank you.